Welcome to the session on ring main system protection coordination as a part of protection and coordination analysis. So in this session, we will understand how the ring main system relays are coordinated with the downstream and upstream protection devices. So now first, let's understand the challenges for coordinating the ring main system protection relays. So in this network, I have shown a ring main system which is being fed from two radial feeders from the upstream at 3.3 kV. And just to understand the coordination of ring main protection relays with the downstream system, I have shown a transformer connected to the ring main system. So as we can see from this relay diagram, since there are two sources, when the fault occurs on the ring main system, each relay will see the fault current from both the directions for the fault on either side of the relay. For example, for fault at cable 3, relay 6 will see the fault current away from the bus D, and for the fault at cable 2, same relay 6 will see the fault current towards bus D. Hence, it is not possible to coordinate relay 6 with one value of fault current, as the fault current seen by relay 6 for various fault location will vary. Also, for the fault at different location, the same relay will see the different value of fault current with different directions, which makes the ring main system protection and coordination more difficult and complex. Now consider an example as shown here. In this case, we cannot keep the same setting for relay 2 and relay 3 and cannot be coordinated with relay 9 because these settings may not hold good for fault at any other location. These settings might work for the fault in this feeder. However, with such concept, we cannot guarantee relay operation for the fault at other location. So for ring main system, you cannot apply the same concept which you are using for radial system protection and coordination. However, we need to make this coordination look like radial feeder coordination without loss of major or entire protection system. So whatever we discussed a while ago, it is demonstrated in this figure. If you keep the same setting of the incomer relays of ring main protection unit, and if there is a fault at outgoing feeder, all the incoming relays of ring main system will trip in 300 millisecond simultaneously, which leads to complete blackout or loss of all connected loads. Hence, these relays should be set to look in one directional only. So as you can see in this figure, the incoming relays are set as non-directional and definite time of 300 millisecond is applied for all the incoming relays to maintain the same protection settings, which does not work in this case. So in order to avoid the nuisance tripping of incoming relays of ring main system, it is advisable to set the incomer relays to look into one direction only. So for this electrical network, the relays connected to the outgoing feeders which are feeding to ring main unit or ring main system are kept as non-directional. However, all the incoming relays of ring main systems will have to be set as a directional protection. So in ETAP, if the relay is having the feature of directional element, then you will see the option where you can check and apply the direction as forward or reverse to make relay look into that direction. So as we have seen in CT polarity section, since the CT polarity is on the upstream side of the CT, we can make this relay look into reverse direction. So as you can see, all the relays are set in reverse direction, or we can say the relays are looking away from the bus. So for the ring main system incoming relays, coordination time interval of 250 millisecond is considered in this case. So for ring main system, the relays labeled with blue color are coordinated with coordination time interval of 250 millisecond. So relay 7 is set to operate at 50 millisecond. Relay 5 is set to operate at 300 millisecond, which is 50 plus 250, which makes 300 millisecond. And relay 3 is set to operate at 550 millisecond. Similarly, the relays shown with the red color, which is relay 2, relay 4 and relay 6 are coordinated and set to operate at 50 millisecond, 300 millisecond and 550 millisecond respectively. So once the incoming relays of ring main system are coordinated, they can be coordinated with the upstream protection relays. So considering 250 millisecond coordination time interval between two relays, which can be relay 6 and relay 8 or relay 3 and relay 1, both these non-directional relays can be set at 800 millisecond. So in ETAP, you can set these relays considering the definite time characteristics and time dial according to the relay operation. For now, I have considered a pickup of 1 which is equivalent to CT ratio. In real case, the pickup can be varied depending on the full load current flowing through the CTs. Now here we will try to understand how the relays will operate for the fault in the clockwise direction. So as you can see, the fault is applied below cable 2, which is shown here. Hence, if we want to analyze the operation of the protection relays connected to the ring main network, the flow of fault current will be in the clockwise direction as shown in this figure. So when the fault is flowing in clockwise direction, the relays marked with blue color will see the fault current flowing in the same direction and those relay will operate. Hence, for this fault, relay 7 will operate in 50 millisecond, and if this relay fails to operate, relay 5 will operate in 300 millisecond as a backup protection relay. Then relay 3 will operate at 550 millisecond, and finally relay 1 and relay 8 will operate in 800 millisecond. So if we create a time current characteristics of all the relays which operates for the fault in clockwise direction, they will be coordinated like this. So for clockwise fault direction, relay 7 will trip in 50 millisecond. Then relay 5 will trip in 50 plus 250 equals to 300 millisecond. Relay 3 will operate in 300 plus 250 equals to 550 millisecond. And if relay 3 fails to operate, relay 1 will trip somewhere very close to 800 millisecond. Now next, let's consider a fault in anti-clockwise direction. So the fault is applied below cable 5. So the flow of current will be in anti-clockwise direction. Now when the fault current flow is in the anti-clockwise direction, as you can see from this figure, the relays marked with red color, which are relay 6, relay 4 and relay 2, will see the fault current in the same directions. Since relay 2 is very closer to the fault, it will operate in 50 millisecond. Relay 4 will operate in 300 millisecond. Relay 6 will operate in 550 millisecond and relay 8 800 millisecond. So if you look at the time current characteristic, relay 2 operates in 50 millisecond, relay 4 operates in 300 millisecond, relay 6 operate in 550 millisecond, relay 1 and 8 can be set to operate close to 800 millisecond. As you can observe from the time current characteristic and the operating sequence of the relays, definite time characteristic is the most suitable characteristic to coordinate the ring main system protection relays. Now let's simulate a fault at various locations and understand the sequence of operation. So if the fault is applied on the transformer primary side below relay 9, you can see from the sequence of operation, relay 9 operate first at 50 millisecond because this relay is set with its instantaneous element to operate at 50 millisecond. Then the associated circuit breaker takes 20 millisecond to operate, which is the circuit breaker opening time defined here. If relay 9 fails to operate, relay 4 will operate in 300 millisecond. Then relay 6 operates in 550 millisecond. If relay 6 fails to operate, relay 1 will operate approximately at 1.1 second, and then relay 8 operates. So if you look at the normalized TCC generated by ETAP for the fault on the primary side of the transformer, which is shown by this fault current arrow as a 1 per unit value, the relays will operate in this sequence, which is already shown as a sequence of operation events. Now consider a fault on connector between CT7 and cable 2. So for this fault location, the relay which is closest to the fault will operate first, which is relay 7 in this case, which operates in 50 millisecond. Then as a backup, relay 5 operates in 300 millisecond. Then relay 3 operates at 550 millisecond. Since relay 8 will see low impedance path to the fault, it will operate before relay 1. So as you can observe from the sequence of events, relay 8 operate first and relay 1 takes longer time because of high impedance to the fault location. Now in previous slide we considered a fault below cable 2. Now if the fault happens above cable 2, as you can see that this fault is considered as a bus fault as there is no impedance between the relay and the fault. So all the fault current will flow through relay 8 only. There is no fault current flowing from the right hand side of the circuit. Hence in the sequence of operation events, you can see that the fault current of 14.38 K is flowing through relay 8, which operates in 722 millisecond as per the provided setting. Similarly, there is a fault applied on connector between CT2 and cable 5. For this fault, the fault current will flow anti-clockwise direction in ring main system protection relays, and hence due to this fault, relay 2 will operate in 50 millisecond, then relay 4 will operate in 300 millisecond, relay 6 will operate in 550 millisecond, and relay 1, which is closest to the fault, will operate before relay 8, which can be observed in the sequence of operation events. This will end our session here. Hope you have found this session useful and informative. Thank you. Hi there.